Okay, in yellow here, we have what? We have a rectangle of with dimensions delta x by delta y down in the xy plane. X-axis going this way, y-axis going that way. And I don't have the point D marked here because it would interfere with everything else, but it's clear what that point would be. And then we have P, Q, R, and S up here, representing the values of some function. Okay, at A, the value, okay, A is the point x, y, so that B, C, and D have coordinates that are easy to write down, you know, x plus delta x, y, and so forth. You have your P, Q, R, and S, and these are labels that we're used to up here. So it's the familiar situation. Here's your picture. So I asked for some characteristics of this polytope because understanding these polytopes is really one of the central things that helps understand a large part of multivariable calculus. Okay? So I started by asking some questions. Now I started by posing a question of a vector such that the slope is fx of xy approximately, or approximately the slope is approximately fy of xy, or a vector such that its rise is approximately df equals fx delta x plus fy delta y. And rise meaning the same thing as delta z in this case. Okay, any vector, the rise is going to be the change in its z coordinate. Okay. I realized pretty quickly that I wasn't going to get good answers from many people, so we had to do an example. Okay, so an example. The example, the length of the vector is f of xy. Okay, what vector has a length of f of xy? What vector could you label on this graph in terms of the letters A, B, C, D, P, Q, R, and S? Well, the value of the function at xy is the z-coordinate of its graph. So a vector from here to here will have a length equal to the z-coordinate, because this is down here in the plane where z is 0, and this is up here where the z-coordinate is the z-coordinate. Okay, so the vector AP has a length of f of xy. Okay, now that should be obvious by this point of the course, but it's not always so. And probably not so for everybody, not as obvious as it ought to be. So we want to clarify how we can notate these things, how we can represent these things, and move on to a little bit of understanding, a little bit better understanding of some of the main things this polytope is related to, which are some of the main things in the course. Okay, so I asked, what's the length of the vector AB? Well, the vector AB goes from here to here. Now you ought to be stopping to think about these. When I pose a question, you know, pause and think about it. See if you can answer it, because you've already heard it one time. See if you've incorporated some of it. If not, make notes, do whatever's necessary. Okay, the vector AB goes from A to B, and the length of the segment from A to B is delta x. Okay, so the length of vector AB has to be delta x. Okay, similarly, okay, now where do we get a vector of length? It might be hard to read this, but it's the square root of the quantity delta x squared plus delta y squared. Where do we get a vector of that length? Okay, well, I got a pretty quick answer from somebody on this one, and it was from somebody that hadn't answered previous questions, so I think maybe people are getting a little bit oriented to this whole thing. And the answer is PR. Is that right? No, it isn't. No, it isn't. I'm sorry, the answer is AC. Yes. Okay. We ask about delta x and delta y. So what do we have? Right here from A to B to C and back to A, we've got a right triangle. And the legs are delta x and delta y. So if you add the squares of the legs, you get the square of the hypotenuse, and the hypotenuse has length equal to the vector AC. Now I write it down. Magnitude of AB is delta x, magnitude of BC is delta y. There's AB, delta x, BC is delta y. AB is perpendicular to BC, so you have the right triangle. And of course the vector AC is AB plus BC. I didn't write all this down. So the magnitude of AC is the sum of those squares. Okay, that comes out pretty, once you see it, it should be pretty obvious. Okay, next question. PQ is in the approximate direction of a tangent line. Okay, well, actually, what I'm doing now, sorry, I'm going back and answering these questions. So, a line where the slope is fx of xy. Okay, so, what is fx? Fx is the, if you want the slope of the vector tangent to the curve at the point A in the direction, well, in the x direction. Well, the vector PQ should be close to being tangent. Now this purple curve that I've drawn here, this might be the values of the actual function when confined to the plane above the line segment AB, vertical plane through the line segment AB. So whatever the function is, it's going to intersect that plane somewhere. So if that's the curve, well then there's the tangent line to the curve. And the slope of that tangent line is the value of fx at xy, the value of the x partial derivative. By the way, that was defined. And that's something I hope everybody understands at this point. Okay. As delta x approaches 0, the 2 points that you use on that curve get closer and closer together. So you imagine shrinking delta x from here down. This polytope would shrink down so that the Q point moves from here to here to here and so forth. Now when the Q point gets about here, the slope of this segment is much closer to the slope of the tangent line, and as you shrink down to 0, the slope of the segment becomes, as the limiting value of the slope of the segment as delta x approaches 0 is the slope of this tangent line, because that's the way the slope of this tangent line was defined. So that it's the vector PQ that approximates the tangent line. So a vector such that the slope is fx of xy would be the vector PQ. Okay. Similarly, say the same thing about PS being approximately slope of the tangent line in the y direction from this point. Okay, so that's going to be your approximate value. It's going to have a slope that's approximately equal to PS. The slope of PS is going to be approximately equal to your y partial derivative. Then the rise is approximately df, which is fx dx plus fy dy. It should have been a dx and a dy, but I used the deltas because that fits with the picture. So the rise, delta z, is this. Now this is where I got a good answer, just from one person, and it was excellent. It was from somebody that wasn't answering most of the questions. Okay, so that's the case. The rise here is fx delta x plus fy delta y, because why? Well, delta x, fx delta x is the slope of this line times the run, which is just the rise from here to here. And then, if you go in this direction, fy delta y is the slope of this line multiplied by delta y. Yeah. Not sure I said it right. The rise of this line segment is the slope of the segment times delta y. Okay, and that's approximately equal to Fy delta y. Well, if you're going from here to here and the rise is Fx delta x, and then you go from here to here and the rise is Fy delta y, then if you go directly from here to here, the rise is your Fx delta x plus your Fy delta y. So PR does have a rise that's approximately equal to your differential. And I've kind of got a picture here. You know, we talk about taking this AC vector here and this PR vector here, which lies directly above it. Since this point lies directly above this, and this point lies directly above this vector lies directly above the AC vector. Okay, we take that and turn it around. It looks like this. Here's your AC, here's your PR, and the rise of the PR is approximately Fx delta x plus Fy delta y, because of what we said before, because of what I pointed out here. Okay, now I asked for a formula for an approximate normal vector at P, meaning a vector normal to the approximate plane. And approximate plane meaning the approximate plane up here at the top, and that's of course the approximate tangent plane. So for some reason I didn't put the word tangent in there. I probably thought I had a good reason, but maybe I should have put tangent plane in there. Okay, well, I think I only got one answer to this, and this should be automatic because this is fundamental to how you construct a tangent plane. And I want to see on the test, I want to see construction. I don't want to see just answers. I want to see steps. I want to see reasoning. When you do the tangent plane, you can take two vectors in the plane that aren't parallel and take their cross product, and that vector has to be perpendicular to the plane. Okay? If you're perpendicular to two lines in the plane, you got to be perpendicular to the plane. So the vector PQ is parallel to the line PQ, and the vector PS is parallel to the line PS. So if you take their cross product, you get the normal vector, a normal vector. I didn't ask for a unit normal vector. I think maybe I'll write that down as a little bonus. Okay, but PQ cross PS, because PQ is approximately in the plane, PS is approximately in the tangent plane. PQ is not parallel to PS, so if you take their cross product, you get the normal. And that goes back to the definition of cross product. Okay, we can define it, or what a property of the cross product, depending whether you use it as a definition or regard it as a property. The cross product is perpendicular to both vectors, and its magnitude is equal to the product of the magnitudes times the sine of the angle between them. That's a fundamental thing, and if WebAssign hasn't drilled that into you, drill it in yourself now. Okay? So, you got this. That's normal to the plane. And a unit normal, maybe don't have room to write it. PQ cross PS divided by the magnitude of PQ cross PS is a unit normal. Okay, now how about a vector whose magnitude is approximately equal to the area of PQRS? Okay, well again, property of the cross product of two vectors is that the magnitude of the cross product is the area of the parallelogram that they define. Well, right here is the PQRS. It's approximately a plane, as long as delta x and delta y are small. It's an approximation to the tangent plane, which we can get using this normal vector, or the unit normal if we don't want to use a unit normal, and often you do. Okay, so this is a section of the, approximately a section of the tangent plane. It's approximately a rectangle. So its approximate area will be the area of the rectangle, defined by PQ, the vector PQ, and the vector PS. So the answer is, if you do PQ cross PS, its magnitude, well, the quadrangle here, PQRS, that we're supposed to find the area of, is pretty close to the rectangle, the parallelogram formed by PQ and PS. PQ and PS are perpendicular because they lie in planes that are perpendicular to one another. So they're so that they form a rectangle. And PQ cross PS, magnitude of PQ cross PS, is the area of the parallelogram they form, and that parallelogram is a rectangle, and it is approximately this rectangle. Okay. Now, somebody answered PQ.QR, so I chose to ask, why is PQ.QR 0? Well, again, PQ and QR are in perpendicular planes, so they're perpendicular. So the vector PQ and the vector PR are perpendicular, therefore their dot product is 0. That's a basic fact of perpendicular vectors. Okay, there's more. Get to it in a minute.